So let's look at an example. How many integers are there from 1 to 250 that are not divisible by 3, 5 and 7? So here we can look at property P as divisible by 3, Q as divisible by 5 and R as divisible by 7, and we want something that the property is not P, not Q and not R. So we can do that. So we have the property divisible by 3. There are 83 numbers like that, which is 250 divided by 3, floor of that. These many numbers are divisible by 5, these are divisible by 7. If I want 3 and 5, then that means it's divisible by 15, so I will get 16 such numbers. 3 and 7, 11 such numbers. 5 and 7, 7 such numbers. And divisible by all 3, I'm going to get 2 such numbers. I wanted to verify why these things are the way they are. And now it's a matter of just plugging in into the formula, and that will give us the answer as 114 numbers that are not divisible by 3, 5 and 7. Let's look at another example. We want to know how many functions from set S that contains 1 through 7 to set T are there that are onto. Now, figuring out onto functions is going to be tricky because we don't know a way to guarantee that the function that we construct will be onto. So what we're going to do is we're going to first look at all possible functions that we have and then remove the ones that are not onto from that list. So why would a function not be onto? A function is not onto if I have this set S, I have this set T, and nothing comes in here. Nothing comes into the element A. If that happens, then it's not an onto function. Or if nothing comes into element P, that's not an onto function. So we can basically create properties in terms of whether A is in the image of the function or not, and based on that we can figure out how many possible functions that we can have that are onto. So we are going to define the property as P, that is functions not having A as an image, Q, functions not having B as the image, R, functions not having C as the image. And what we are looking for are functions that don't have the property P, don't have the property Q, don't have the property R. That means A is in the image, B is in the image, C is in the image, and that's exactly what we want for a function to be onto. So to do that, first we are going to find all the functions that can exist, number of functions that have the property P, namely not having A as an image, same with Q and R, then having property P and Q, and that means not having A as an image and not having B as an image, so on. And finally property P, Q and R means I don't want A, B or C to be in the image. So let's first look at how many functions we can have. So we have here, there are 7 elements that I have in set S. So let's look at one of the elements in here. There are 3 possible choices I have, either map it to A or map it to B or map it to C. And this choice I have for every element. So total number of functions that I'm going to have is 3 to the power 7 because I have 3 choices for 1, 3 choices for 2, 3 choices for 3 and so on. So total number of functions I have is 2187. Now let's look at functions that have the property P, that means A is not in the image. If A is not in the image, that means element 1 now has only two choices, either B or C. And the same thing is going to happen for 2, same thing is going to happen to 3, and so the total number of functions we have is 2 to the power 7, and same thing is going to happen for NQ and NR. If I wanted to have property P and Q, then that means I don't want A to be in the image, I don't want B to be in the image, then there is only one function that I can have because everybody has to map to C. And the same thing for N of P and R and N of Q and R. Finally, if I wanted to have all three properties, that means A is not in the image, B is not in the image, and C is not in the image, that means I have no functions that I can write because one cannot map to anything and that's not allowed in a function. Now it's a matter of plugging in, and that will give us the answer as 1806. I wanted to check why each of the number came out the way it did and how we got the final answer as 1806. Once again, we have reached the check before you go ahead slide. So what we did in this video was we looked at some applications of the inclusion exclusion principle. So I want to make sure you have understood how we split the problem into inclusion exclusion principle and how we found the answers to each of the problem at hand. We have reached the end of the module. At this point, I want you to go ahead and do the review quiz.